Welcome to this lecture series on marine hydrodynamics. In the last class, we are talking about unsteady flows, basically viscous incompressible fluids and flow is laminar. Here also the flow is unidirectional, or we can call this as a fully developed flows. In the last class, we have talked about flow on a single plate due to the single plate oscillation, either the translation, oscillatory motion or transient motion. Then we have talked about Contd flow, both the case of transient motion as well as oscillatory motion. Today, we will continue the unsteady flow by considering another case, that is the what happened to the Poisson flow. Poisson flow. First, we will consider the Poisson flow, unsteady Poisson flow, basically unsteady Poisson flow. So, here also we will have two cases, one is the oscillatory motion and the other is the what we call oscillatory Poisson flow, or another is the transient motion. So, in case of oscillatory motion, we assume first we will concentrate on this. So, in case of a Poisson flow, here we have non-zero pressure gradient, that means we have two plates, y is equal to 0, the other is at y is equal to h, these are the two plates, and here the plates are fixed. So, we have no slip condition, it is like a channel, you have the no slip condition, and we have, so the flow is unidirectional. So, we have u is equal to u by t, like what we have discussed earlier, and we have v is equal to 0, w is equal to 0, and again in this case what we have del p by del x is not equal to 0, and then in the process what we get, we get del u by del t becomes rho del u by del t minus del p by del x plus del square u by del y square. This becomes my Navier-Stokes equation of motion, and as then the boundary conditions will be, because the flow is, I assume the flow is oscillatory, the boundary conditions will be u is equal to 0 at y is equal to h, t is greater than 0, and u is equal to again 0 at y is equal to 0, t is greater than. So, at both the walls there is no slip condition. Further, we have del p by del x, we assume that del p by del x is of this form, or del p by del x is, because there is a minus, I will assume minus a, call it a sin omega t. If I assume this is oscillatory in nature, the pressure gradient is oscillatory in nature, which is non-zero, then what will happen to the flow? One can easily, if I substitute for del p by del x is a sin omega t, then I will get u x t, u y t rather, it can be obtained, u y t will be of this form, it can be easily check that I am minus a e to the power minus I omega t by rho omega plus or into this is called 1 minus cos hyperbolic minus I omega by nu to the power half into y minus h by 2 divided by cos hyperbolic minus I omega by nu into power half into h by 2. And one can easily see that if you take this form of the solution, then one can easily see that when y is equal to h, this will give me total will give me y is equal to h means this will give me 1, 1 minus 1 will be 0. Further at y is equal to 0, y is 0 means again this will be again h by 2, y is 0 means minus h by 2 same as h by 2, and then this will give me 1 and 1 minus 1 is 0. So, these two conditions will be satisfied, and further, so this will be the, and again we can see that this equation is satisfied u by t. So, this becomes the full solution in this case, and it may be noted that here I square is chosen as minus I root over is chosen as e to the power 3 pi by 4, 3 pi I by 4, that is what is chosen in this case, and that comes from the physical requirement. This is the solution associated with the Poisson flow in case of oscillatory motion. Now, let us look at what happened in case of transient motion in case of a Poisson flow. So, if I look at the transient motion, basically for the Poisson flow, now in the same case we proceed in the same manner. The two plates are fixed, and here this is at y is equal to h, and this is at y is equal to 0, and we have already chosen q bar is equal to u I hat. So, you have u is equal to u by t, and we have p is a function of p x only, or rather because it is unsteady motion, p is a function of x t, and then we have our Navier-Stokes equation of motion gives, it is just like the previous case, only the we have del u by del t rho minus del p by del x plus mu del square u by del y square. This becomes the equation of motion, and here since now we are looking at the transient motion. So, what will happen, the solution and the boundary conditions here are also u is equal to 0 at x is equal to 0, u is equal to 0 at t is equal to 0 and y is greater than 0. So, initially the transient motion, initially at time t is equal to 0, u was 0 and u is equal to u is equal to 0 at y is equal to 0, t greater than 0, and again 0 at y is equal to h, t is greater than 0. So, this becomes the, so initial condition, this becomes the initial condition, and this 2 becomes the boundary condition. So, this is the IC and these are the boundary condition, because this gives that at the two walls there is no flow, and this gives at time t is equal to 0 there is no fluid. Thus, here it is coming from the no flow condition at the time t is 0. So, at t is equal to 0, y greater than 0, this is 0, and here at y t is greater than 0, y is 0 is also 0. So, now we will look into the type of solution it has. So, if you look into that, then what will happen, and I have, so what I will do, like earlier my total u, the velocity will be us plus, and this us is a function of y plus ut, that is a function of y and t. That means, this is the steady motion and this is the unsteady motion. Basically, this is the time dependent motion, time dependent part. So, this is unsteady, this is steady. So, if I substitute for u equal to, then what will happen to my u satisfy, because when we have unsteady motion we have seen that my u s satisfies rho del u s by del unsteady motion. In case of unsteady motion, in case of unsteady motion, my u s satisfies rho, u s satisfies del square u s by del y square equal to minus or plus del p by del x into mu, and if this satisfy u s satisfy, then what will happen to, because u is equal to u s plus u t, if u is equal to u s plus u t, then what happen to u t? U t will satisfy, it can be easily seen that u t will satisfy rho, that is del u by del t, rho del u by del t equal to mu del square u t by del t square del y square. So, this becomes my u t will satisfy, because if you add these two, then you will get it. So, u t will satisfy this equation. Now, if you look at the boundary condition and the initial condition, we have given u is equal to 0 at t is equal to 0, y greater than 0, and our u is equal to u s, u is equal to u s plus u t at t is equal to 0, y greater than 0. So, which implies u is 0 means, that means my u t becomes minus u s at t is equal to 0, y is greater than 0. So, that means at time t is equal to 0, the time dependent unsteady motion is same as the steady state solution. On the other hand, when that is u t is minus u s, further we have, because we have the, if you look at the boundary conditions on the wall, our u is equal to u t plus u s, and u t is already, u s is 0 in case of a steady motion. So, that means again u is 0. So, that means u t is also 0 at y is equal to 0, further y is equal to h, and for all t greater than 0. So, this becomes, so in the process what will happen to my, so in the process my u t becomes, so u t will satisfy rho del u by del t equal to mu del square u by del y square, and then u t is subject to the boundary condition, and we have u t is equal to u s minus u s at t is equal to 0, y greater than 0, and u t is equal to 0 at y is equal to 0 comma h for t greater than 0. So, this becomes the initial boundary value problem associated with the u t. On the other hand, what will happen to u s? U s is the solution that is associated with the unsteady motion, unsteady Poisson flow, and we have just the earlier we have just obtained in before 2 classes, we have just obtained the Poisson flow solution, and that solution is nothing but 1 by 2 mu del p by del x into y square minus h y. This is the solution. If I have a, that is my u s. So, if I substitute this u s, this is a and this I call. So, I substitute for u s in this one, then I know the initial condition at u t, and if I do that, then and apply the method of separation of variable to this problem, I substitute for u s from b in the initial condition in a, and after substituting, if I apply the method of separation variable if apply method as separation variable, then your ut will obtain, that means the solution of this A we obtain as it is of this form sigma n is equal to 1 to infinity a n e to the power minus n square pi square nu t by h square into sin n pi by h into y. This becomes my general form of solution where a n's are to be obtained, and a n's are to be obtained because you can see that this ut satisfy both the boundary condition at y is equal to 0, this becomes 0 at y is equal to s, and but ut is minus us using this initial condition where us is given by this. I can obtain what exactly, because I also have these functions sin n pi by h y is, these functions are orthogonal functions. So, that will give me my a n, and that will give me my a n as minus 0 to h u s, because I am substituting here ut here u s, that is a function of y into sin n pi by h y dy divided by 0 to h sin n pi by y dy sin square n pi by y dy. And if you simplify with this, result, then substitute for us from here, and that will give me a n as minus 2 by b mu 2 by h mu to del p by del x to the power half del p by del x into h by n pi cube 1 minus 1 to the power n, and this is my n. These are the n's. So, once n's are known, so after ut is known, and once ut is known, so my u is nothing but us plus ut. So, the full solution is obtained in this case also. And so, this is the case of the unsteady solution. So, we have seen the two cases of unsteady solution, particularly when we have there are two plates or two flow between a channel when the motion is unsteady, and also we have seen the case of when just a plate, infinite plate, which is oscillating either transient or oscillatory. So, we have seen that unsteady case, and these are all some of the worked examples for fully developed flow associated with unsteady motion. With this, I will just let me go for another case which is a little more complex, but I thought I will derive it. That is what the problem is called the diffusion of a vortex sheet. Here what exactly happened? Like we have seen that when we have a plate, the plate was oscillating, that is a transient motion, and only we are looking at the flow that was when y is greater than 0. What will happen if the plate is oscillating and this plate is oscillating and we have fluid in both the direction? This plate is oscillating and we have fluid in both the direction. There is a transient motion of this fluid, and this is a, so here what I will say that basically I look at there is a no pressure gradient. So, I have del v by del t, the unidirectional flow without pressure gradient. So, del v by del t is minus is nu into del square u by del y square, and here what I propose that as I say that plate is oscillating in such a way that y uy0 time t is equal to 0, y0 means at a t is equal to 0, this becomes u naught for y is greater than 0 and minus u naught for y less than 0. So, this is oscillating in the positive direction, y greater than 0 means the plate is oscillating in this way, and if it is y less than 0 as if the plate is moving in this way. So, the plate is moving for y greater than 0, the motion is in the plate is moving in the positive direction, whereas the fluid is moving in the positive direction, whereas for y less than 0 the fluid is moving in the plate is moving in the positive direction. And then as usual this is the initial condition. Apart from the initial condition, we have u at infinity t is u naught and u at minus infinity t is minus u naught. So, this is for y greater than 0, this is for t greater than 0, and this is for also t greater than 0. So, so I have one initial condition at t is equal to 0, there are so fluid motion is this, and at infinity this is the motion is like this. So, then just like what we have done for the transient motion for the Stokes problem in the similar manner, particularly Stokes first problem, then we have substitute by u naught is equal to f of eta. We will follow the self similarity solution approach as we have done. This is why in the case of a single plate which is oscillating, then eta is this, then as we have done, I just follow Stokes approach, Stokes first problem, here a single plate which is oscillating, same approach I will follow, then I will obtain f double dash is equal to minus 2 eta f dash, and here the conditions at infinity we can see that f plus minus infinity will give me plus minus 1, and further I will have, so this will give me to this boundary condition. So, that means I am looking for the solution of this equation subject to this boundary condition, and this will give me, if I look at the solution of this will give me f of eta f eta. I am just following the notation of Stokes first problem, that means when I have one single plate which is making transient motion, and then you will see that u is equal to u naught f, that is eta is y by 2 root over of nu t. This is the kind of solution we will have in this case. Here Stokes first problem from, rather I will say from Stokes first problem. And if you look at the flow, in fact we have seen that the flow will be like this. Something like this. It will not touch the line, but it will be, and one is for various cases, because the positive as you go away from this plate, this becomes u naught, here it will be minus u naught, and again on this side u will be u naught, this plate will be moving. So, this is the way the fluid u will look like, and from this if I look at the, because what will happen to, this is a kind of flow where what will happen to the flow, what is, look at the vorticity, the vorticity will be del u by del y minus del v by del x, and v is 0. So, it will give me del u by del y. If I look at this, then it will give me u naught by nu t into the minus y square by 4 nu t. and del u by del y will be giving me this. Then again if I look at the total vorticity, this is the vorticity at any time. Any time t, what total vorticity, and that will give me minus infinity omega dy, and it can be easily seen that if I substitute for these values of omega here, then this will give me 2 u naught. It can be checked. So, the total vorticity and which is independent of time. So, this example shows that the flow is there is a, it is no more a vortex free motion, it is a, there is a vorticity is non-zero, and total vorticity at any point the vorticity is given by this, whereas so it is a rotational motion. So, motivated by this that in case of a unidirectional flow we can have vorticity. Now, let us go to derive one of the very important result, that is called vorticity transport equation. Equation for a incompressible fluid. So, basically if the flow is a 2 dimensional, because we have seen that when the flow is incompressible and viscous, even if the flow is laminar, if flow is unidirectional, the vorticity is non-zero. And now, let us look at the vorticity transport equation. Basically what will happen when the flow is incompressible and viscous, then what will happen to the vorticity equation. So, we have two equations. Basically let us consider this as the fluid is flow field is 2 dimensional, if I have the flow field 2 dimensional. So, we have from continuity equation, we have del u by del x plus del v by del y is 0. If I assume that I have a psi, the stream function that exists, because the flow field is 2 dimensional, I can have a stream function psi. The stream function psi exists, then I will have u is equal to psi y and v is equal to minus psi x, we all know for a fluid flow. If this exists, then what will happen to omega for a 2 dimensional flow? That will be nothing but del v by del x minus del u by del y. If I do this, and my v is what? V is minus psi x. So, this will be del by del x, v is minus psi x minus del by del y, u is psi y, and that gives me minus del square psi, because this gives me minus del square psi by del x square plus del square psi by del y square, thus omega is equal to minus del square psi, j omega bar you can call it. And this is so, unlike the case of a irrotational motion, in case of a incompressible fluid where we say the flow is irrotational, is to say del square psi is 0, but here when the flow is 2 dimensional and we have fluid is incompressible, and basically I have not yet covered. So, for incompressible fluid the vorticity satisfy this. Now, looking at the, if you look at that comes from the continuity equation. If you look at what will happen in case of the equation of motion, particularly in the case of incompressible invisible fluid, the equation of motion becomes, we have rho del u by del t plus u del by del x plus v del by u del u by del x plus v del u by del y, that is equal to minus del p by del x plus mu del square u by del, rather I will call it del x square plus del square u by del y square, this is x square. Similarly, I have the y component will be rho del v by del t plus u del v by del x plus v del v by del y, and that is minus del p by del y. I have observed the body forces in pressure plus mu, I can call it del square v, it can be also called del square u. So, what I will do, I operate the first equation by del y and second equation by minus del by del y. If I do that, just operate by del y the first equation and second equation by minus del by del y and add 1 and 2, rather I will call it this is equation A, equation B, operating by del y operating A by del y and B by minus del by del x and adding. If we add this, then what will we get? We will get rho into del omega by del t plus u del by del x omega plus v del omega by del y, and that will give me nu, because these two terms basically you will see that the pressure terms will be eliminated, and that will be nu del square omega. This becomes the equation, and in fact this is called the vorticity transport equation. So, the two equation of motion reduces to a single equation. So, in case of when you have vorticity transport equation, the equation of motion becomes a single equation. So, the three equation, one is the equation of continuity and the two equation of motion reduces the three equations and reduces to two equations. And another thing is that in case of the vorticity transport equation, this is this provides the complete flow field. This gives the complete description of the flow field. So, this omega, when the motion is small, even if the motion is small, the omega is undisturbed, because even if I say omega is small, this equation, because u is there, omega is only one term. So, this equation even for okay. So, and another thing here I want to say that the when near a wall, omega is large, it can be seen that this is one of the important observation. So, basically when you have a flow around a body, then we will see that just near the wall there will be the vorticity transport, the vortex formation will take place and they will propagate. So, there is a formation of vortex takes place just adjacent to the wall in case of a laminar flow, and this vorticity, this vortex that is formed, that vorticity that is produced near a wall, that starts propagating in the flow direction, and that is similar to that as if the energy transfer from a heated surface. So, what happened, again I will repeat this: near a wall the vorticity that will be produced, particularly when omega is large, near a wall omega is becoming, the vorticity becomes large, and that vorticity it get transported along with the fluid, and this the energy associated with this, it is similar to as if a heated surface is that like the transfer of energy in a heated surface, that is the way vorticity transfer takes place. And with this understanding, I will, because we will come to this vorticity transport equation little in detail about when we will talk about boundary layer theory, because the formation of vortex formation takes place, and even if as we go away, when we will see that in case of boundary layer theory how vortex shading and flow, vortex shading takes place, vortex shading and flow separation takes place, that will come as a part of the when we will look into the boundary layer theory. Now, with this equation of vorticity equation, now I will go to, just let me summarize some of the results. I will look into the summary of some of the results what we have discussed today, and in the case of the flow associated with the, just I will first briefly summarize what all we have discussed. So, I will call it summary of viscous unidirectional flow. In fact, when I started the unidirectional flow, I say the Reynolds number is greater than creeping flow motion, the Reynolds number associated with the rather I will say Reynolds number for RE for unidirectional flow is greater than RE for creeping motion. However, basically when the motion is slow motion. So, even if it is R is greater in this case, but still the R is small, because here again we are also not considering the convective inertia term. R still is small, because convective inertia term we are not including here, and we are again considering the flow is unidirectional in this case, but for the fully developed flow. We concentrate two types of problem. The first type we call when one wall is, first we talked about there are two cases, suddenly accelerated plate flow due to a suddenly accelerated plate, and then we also talked about, and particularly so suddenly accelerated plate in an infinitely extended fluid. And this problem is referred to as Stokes first problem. Basically, we have only one plate which is oscillating at the time t is equal to 0, suddenly there was no speed and suddenly it starts to oscillate. And then we looked into a case of flow near a oscillating flat plate. That means, in this case flow was transient, that is infinitely extended plate where the flow was transient, and in this case again the plate was there, but the flow was oscillatory in nature. Because the flow was oscillatory, and this problem is called Stokes' second problem. And then we talked about the third category of problem we talked about today, that is a what I call this diffusion decay. Today I talked about what vorticity diffusion equation I talked about today. Okay, so then I have another problem we talked about, flow between fixed wall. Flow between wall. Two walls, basically flow in a channel. And here we also talked about when the walls are fixed, both steady and unsteady solution we talked about. In case of unsteady problem, we talked about which flow which are transient or oscillatory, and in case of and there are flows which we have considered called Stokes, that is Contd flow, generalized Contd flow, plain Contd flow. Then we talked about generalized, again we talked about Hagen-Poiseuille flow. Then we talk about, we have talked about generalized, in these two cases we have talked both steady and unsteady motion. Then we have talked about Hagen-Poiseuille flow, we have talked about Hagen-Poiseuille flow, and after Hagen-Poiseuille flow we have again talked about generalized Contd flow. So, all these cases we have been able to get closed form solution. And closed form solutions where there are few problems, and in fact we have assumed the flow is unidirectional or fully developed flow. Now, there are other flows like if you look at flow through porous media, basically which is based on Darcy's law. Basically Darcy postulated this formula, but Darcy's 1856 gave the postulated on a formula for flow through porous media, and that formula says q bar is equal to varies as grad of p, that means q bar equal to k by mu grad p, where k refers to the permeability of the medium and mu is the viscosity, dynamic viscosity of the fluid. So, in this basically when we look at the flow in rocks, or even if we will see that when flow passes through some structure, porous structure, they will follow this characteristic. It was the first one which appropriate for linear, assuming motion is slow. So, this is was a case of then another type of flow, because all these three, our flow is based on Stokes postulate. as we have mentioned, the Navier-Stokes equation is based on Stokes postulate, and these are called all Newtonian motion, Newtonian fluid. It is not necessary that all flow will follow Newton's law or Stokes postulate. There are flows which will not follow Stokes postulate, and we call this kind of fluid as non-Newtonian. There are various types of non-Newtonian fluid, but we are not going into such details, but I say that the fluid which is the Navier-Stokes equation is based on the Stokes postulate, and these fluid are Newtonian fluid, and there are other fluid. The fluid which will not follow the Stokes postulate will be called as non-Newtonian fluid. Basically, then we have talked about actually 3 different methods. Basically, all these problems were talked based on 3 major methods, analytic methods of solution. If you look into, we have based on 3 methods. Basically, one we have talked about similarity transformation method, method of similarity transformation. And this method, in fact, this is one of the method which is reduces the dimension of the problem to a large extent, and of course, this is there are certain condition to be followed for the flow. On a certain condition is required when you have to follow the similarity transformation, but this is one of the advantage is that of this method is that it reduces the dimension of the problem by 1, and basically this is more suitable for large class of problem for laminar flow can be handled by this. And another, in case of oscillatory method, for oscillatory flow the problem leads to boundary value problem only, and having a non-homogeneous, it becomes a non-homogeneous boundary value problem, and it becomes very easy to solve. We have what we have seen in case of simple problems. And then another aspect of this, the 2 kinds of flow what we have discussed, that is steady and unsteady. In all the cases R is small. Our concentration was on unidirectional flow, and also R is small, we have taken the convective terms, we have neglected convective inertia term. Then, and these flows are called laminar. As I have already mentioned, for a laminar flow, the flow follows certain direction and follows a regular path. The flow can be transient, it can be oscillatory, it can follow a steady path. This is oscillatory, this can be a transient motion, and can follow a uniform speed, uniform flow. So, the 3 cases for laminar flows, and this oscillatory flow, it follows a periodic pattern, and this is a uniform flow or steady flow. Basically, this motion is steady. That all becomes in case of laminar flow, and when Reynolds number is large, small. There is a large class of problem, particularly if you look at, if I say that non-convective term, convective inertia term is not, convective inertia term is not equal to 0. there is a large class of problem where the convective inertia term is not equal to 0. In such situation, the flow will exist, the components of UVW will exist, and in fact, large class of problem can be handled on this, and in most of the cases it is the Reynolds number is moderate in nature. There are moderate in nature RE Reynolds number, and large number of, and here the closed form solutions may not be possible, and most of the time we go for numerical solutions. And even if although we go for numerical solutions, and in this case the flow can still remain laminar, but again, so this is here the Reynolds number is moderate. On the other hand, again sorry, for large Reynolds number, this when Reynolds number becomes large, then what will happen? There is a boundary layer theory. Okay, so before going to that, when the Reynolds number becomes large, then there is a transition to laminar comes. Like suppose we have a flow which was initially going on a steady flow, when our Reynolds number will be large, then suddenly there will be disturbances will be formed, and this is called the transition intermediate. As the Reynolds number goes on increasing, this is a transition to laminar flow occurs. And beyond that, when the Reynolds number becomes extremely large, then the flow pattern they will not be again for basically for a very large Reynolds number, the flow will be very, it is random, and particle does not follow any particular path, and then the flow we call is as a turbulent. Basically again here, in fact, there are situations when this Reynolds number is large, that varies from case to case. The question comes how large it can be, how large the Reynolds number can be, RE can be, and this all depends on the nature of the physical problem one is dealing with. So, and this Reynolds number, because it can go up to 10 to the power 6, 10 to the power 5 that order, and it can be more than that. And even if there are situations, particularly when you look at a flow on a flat plate laminar flow, again we have in between this in this large Reynolds number we can have a situation where we have boundary layer, formation of boundary layer that will take place. And in the next class we will talk about how the boundary layer formation takes place, what is boundary layer thickness, and how the equation of motion, particularly the laminar boundary layer, the laminar flow what we have discussed, or the equation of motion for viscous fluid, how it will change when there is a formation of the boundary layer. And then beyond boundary layer, when the Reynolds number goes increases further, then we will see that turbulent flow becomes turbulent. So, let us stop here. In the next class, we will emphasize on boundary layer theory. Thank you.